Hi, so this is lecture 17. I want to mention one little fact that might be useful for you when you do some problems on the homework. And this is a reminder, you already learned this in Phys 2, that whenever there is a two-slit interference, and let's say we have a geometry where the coordinate y is measured from this central point right here, and this is the angle theta from the center. The location of maxima, max locations, the angles at which the maximum happens, are given by d sine theta equals n lambda, where d is this distance, the angle, the theta is this angle, n is 0, 1, 2, lambda is the wavelength. And also you can see that y over L equals tangent theta. So L would be this distance right here. Where do these formulas come from? They come from thinking about the two paths that lead to a particular point, and that in order to reach a maximum, the difference in the lengths of those two paths have to be either integer wavelength, one wavelength, two wavelengths, or zero wavelengths in the center. So that's where this formula comes from. And similarly, if you have a one slit diffraction, now A is the width of the slit. So actually, let me make this a little bit bigger. Yeah, like that. In this situation, you also get a pattern. I guess maybe I should add that in this situation, you get a pattern that's periodic, right? Periodic pattern of max and min. So it's the intensity that I'm plotting. Intensity, brightness. In this situation, you also get a pattern that has a central peak, and then there are there are satellite peaks. Not two. There's infinite number of them. Maybe not infinite number, but there's many peaks. Sorry, not infinite number, but there are many peaks. There can be many peaks. And so now here, there is not a formula for positions of maximal points. Again, with the same geometry. So here's y equals 0. Here's the y equals 0. And I'm measuring y in this direction. Again, I can measure angle theta. And so these are locations, min locations, locations of the intensity minimum now. They are given by a formula that looks the same, but this is a formula for positions of minima. There's not a formula for positions of maximum for a single slit diffraction. It's a much more complicated expression. You have to do integrals, never mind. But there is a formula like that. Again, n equals 1, 2, 3, and so on. And again, y over L equals tangent of theta. There is actually a formula for the min locations in the double slit situation. It's given by d sine theta equals n plus 1/2 lambda, where n is 0, 1, 2. So this says that path length difference has to be half a wavelength apart, half a wavelength, 3/2 wavelengths, and so on. And the maximum says that path length difference has to be 0 wavelengths, 1, 2 wavelengths, and so on. And the single slit scenario, minimum locations happen where the second formula, a sine theta and lambda, applies. And also implicit here is that when we talk about the two-slit interference, the widths of slits are ignored. If the slits have finite width, then the pattern is more complicated than just this periodic series of max min, and it's kind of a combination of two effects. You don't need to worry about that, okay? But implicit in the two-slit interference is that in the two-slit interference, we can ignore the slit width, and in the one-slit interference, that's not possible to ignore. It's kind of essential. and then the second formula applies. Okay, so this is just an aside. I understand that our current discussion seems too conceptual and it's not comfortable for you. You want formulas, you want equations. What we're doing right now is we're starting from scratch. You're literally a newborn right now, and we are we're setting a completely new stage. So before we can even talk about calculations, I have to set the stage and explain what is it that we're going to be calculating in the first place. Like, what is there to calculate? One thing that we did talk about so far is that you can use wave aspects in order to predict probabilities of where particle impacts will be found. Wave aspects, you already know. You know what happens to light when it goes through two slits. The classical wave aspect of light can be reused, it can be reinterpreted to give probabilities. And the same applies for particles. So now what I'm going to do is I'm going to summarize the content of yesterday's lecture. I'm going to take it one step further. And in the next lecture, we're going to transfer everything that we've discussed here to things that we traditionally think of as particles, such as electrons. And we will see that the groundwork that we've laid using photons as a stepping stone will be very easy. It will be very useful for going over to other things like electrons, neutrons, blah, blah, blah. Okay? Okay, so here we go. So first, a quick summary of yesterday. Big picture. We started by saying that, look, we have evidence that light is made of particles. And we say, wait a second, but then how do you explain the two-slit interference, the one that we see with light, like in Physics 2, Experiment 5? So we had to try to understand how we can reinterpret interference results given that light seems to be made of particles. One potential idea is that that happens due to interactions between light particles, between photons. Okay, fine, then we eliminate that possibility of interactions. Whether photons actually interact or not, that's irrelevant. We can eliminate that possibility completely by sending one photon at a time. When we do send one photon at a time, we actually do see individual impacts, buttressing the notion that light is particles. But then something funny happens. When we accumulate enough photons on the screen, we get back the two-slit pattern as if there is something interfering. But we were sending one photon at a time, so what could possibly be interfering? And the upshot of that discussion was that, yes, while photons are particle-like entities, we have evidence for that from photoelectric effect, from Compton effect. That was the whole point of Compton effect, that we really treat it like a particle. It's not, while that's true, it's not right to think of it as a classical particle, i.e. one that follows trajectories in space. Because if it did follow trajectories, the kind of pattern that we would expect from sending one photon at a time is maybe two lines or two peaks behind each slit. Because, you know, the trajectory is a straight line and boom, the photon hits next to, at the level of one of the slits or at the level of the other slit. So we would have expected something like this, top picture with two slits, and we would expected something like this bottom picture if one slit is closed. Instead, the accumulated pattern of dots, the accumulated pattern of localized impacts with two slits looks like this. We get back the two-slit interference pattern even though we're sending only one particle at a time. And with one slit, if you cover one of the slits, you get back another type of interference pattern. You get the one-slit diffraction pattern. With one, you get the classical pattern that you would expect with a one-slit diffraction. So we have to step away from the trajectory picture of particle motion. And second, we see that process is inherently random. We can only predict, we can only talk of particle landing location probabilities, which is completely incompatible with trajectory view of particles. With trajectories, if you know initial conditions well enough, there are no probabilities to speak of. Here, even if we make the experiment perfect, the outcome is still random. This is a very important idea. And at the end, we said, wait a second, if the accumulation pattern matches what we would expect from a wave picture, perhaps we can reinterpret the wave aspect of light. Perhaps we can use that wave aspect of light for predicting probabilities of where photons land when they are manifested as particles. So photon manifests itself as a particle because it creates a localized impact. And we also see that the effect is random, so there are probabilities to talk of. So perhaps we can use what we know from wave theory, from classical wave theory, and reinterpret that as something that can give us probabilities of where we would find a photon when it does create a localized impact, when it does manifest, when light does manifest itself as a particle, as a photon. So let me summarize that now. Let me canonize that. So this is standard interpretation of wave-particle duality for light. And then we will wane off light. The goal is not to build a course around light. Light is a relativistic thing, concept, object. It requires much more advanced physics. I'm only using light as a stepping stone because the first evidence for wave-particle duality, i.e. the photoelectric effect, naturally came from light. It was an effect about light. So we had to deal with that, and we had to try to make sense of how the wave-particle duality works for light. Once we make sense of that, we will move on and we will not come back to light. This course is not about light. Actually, even the relativistic section is not about light. Speed of light is just an archaic term. Anyway, here's the standard interpretation of wave-particle duality for light. So point number one, and I've already kind of led you to this water. Now we're just going to drink this water. So point number one, summary, is particle and wave aspects of light are inseparable. They come together. That's the duality. So in other words, light behaves simultaneously like a wave and like a flux of particles. Everything that I set up to now fits this duality viewpoint. of quantum aspects of light. And the classical wave description is useful, and it enables us to calculate the probability of the manifestation or expression of light as a particle. Maybe I should say probabilities. No. I think what I wrote here might be a little bit vague. So in other words, when particle does manifest itself as, I'm sorry, when light does manifest itself as particles, photons, individual impact events, ping, we can use classical description of light to calculate, for instance, the probability of where that single impact event happens. That's what I mean by this. Point number 2, predictions about the behavior of photon can only be probabilistic. I'm reiterating. And therefore, the notion of a trajectory, when we think of particles, classically, we think of trajectories. Now we introduce probability as being essential to this weird particle, and therefore we can no longer think of trajectories. Point number 3, the information about the photon at time t is given by a wave, electric field, which is a solution to classical Maxwell equation. And we would say that this wave characterizes the state of the photon at time t. From this wave, we can get the probability of observing a photon at time t and some location x, y, z. One advantage of starting with photons is that when I talk about a wave, I can make it very concrete. What wave am I talking about? And that wave is electric field. You're familiar with electric field. And this electric field, well, it's defined at every point in space, x, y, z, right here, and at any moment in time. So I point to a point in space and some time, and at that point in space and some time, there's an electric field at that point. Don't worry that it's too abstract. Don't worry that you don't know how to calculate it. You don't need to. At this point, I'm just asking you to embrace the fact that at any point in space and time, I can define an electric field. And this electric field will be useful for computing probabilities of finding a photon at that point or around that point in space when when the position measurement of that photon is performed, when I'm asking photon, where are you? There's a probability that it will be found there. And this electric field is a device that can give me probability of finding the photon. So folks, don't be nervous about the fact that I'm using really big words like Maxwell equation. I'm not going to ask you to solve Maxwell's equation. What I'm trying to say is this E comes from classical physics, for example, Maxwell's equations. And we can use that classical information for predicting the quantum manifestation of light, i.e. probability of where the photon is found. That's what I'm trying to say. Then I will take all this and I will upgrade it to other things like electrons. That's why I'm doing this. So we say that this wave characterizes the state. I will explain what that means of the photon at time t. What I mean by the word the state, like it sounds too abstract to many of you. If I have classical motion, like baseball moving through space, planet moving through space, the state of a classical particle is determined by its current position and current velocity, or position and momentum. That means that if I do specify its current position and current momentum or velocity, then I can make a prediction for where that particle will be at any point in time. So if you want to know if the asteroid is going to hit the Earth, what you need to do is you need to know its position and velocity. And of course, you also need to know what it's interacting with. That's implicit. And the knowledge of position and velocity is sufficient to predict whether the asteroid will hit the Earth or not. So state of something is the minimal amount of information that you need in order to predict the properties of that something. That's what the word state means. For motion, for classical motion, a state is determined by, state is set by position and velocity of a particle. If you know position and velocity, you can predict everything else you want to know. There is another example of the usage of the word state. You may have heard the classical equation, or you may have heard the equation of state of a gas, ideal gas, equation of state. That might ring a bell. So what that says is, if you give me pressure, volume, and temperature, and density of the gas, I can answer any question about that gas. So again, in that context, the word state means the necessary information that you need to specify about the system in order to answer any other questions you might have. When we talk about quantum mechanics, when we go to quantum mechanics, we have to upgrade our notion of state of a particle. In classical mechanics, the term, the state of a particle is defined by its position and momentum. Because if I know its position and momentum, I can calculate trajectories. In quantum mechanics, we cannot talk of trajectories. Quantum mechanics is inherently probabilistic. So something else must replace position and momentum. Some other piece of information is needed in order to extract anything else we might want to know. And what we can ask in quantum mechanics is we can ask probabilities. Asking for a probability is a good question in quantum mechanics. Asking for a trajectory is not a good question in quantum mechanics. So therefore, in quantum mechanics, the state of a particle is some kind of a mathematical entity that will allow us to calculate probabilities. Okay, so I hope that what I said now makes a little bit more sense of what I mean by a state of a particle. And in the third segment of today's video, I come back and do another pass to try to clarify that even further. State of a classical particle versus state of a quantum particle. And I would like you to, I will try to grow your comfort around this notion. So the last thing that I wanted to say is the probability of observing a photon. So like, how do you use this E? I told you about E, the electric field. Like, what about it? I just told you that it's we have to focus we have to shift our mentality to probabilities. Well, fine. How do I get that probability? For photon, the probability of observing it at a given time t and location x, y, z, point in space, is proportional to the square of the magnitude of the electric field. So that's the brouhaha, how we use the electric field. For this problem, I didn't have to solve Maxwell's equations. I took a shortcut. It's a very simple enough problem that I treated each slit as a source of spherical waves. Once I know that these are spherical waves and I know their wavelength, I don't need to solve Maxwell's equations. The waves, the little waves that I drew yesterday, you know, you have a little wave coming from here and a little wave coming from here and they meet, that is the electric field. I just didn't have to solve Maxwell's equations to find it. But we did use the electric field. And this blue thing right here is the intensity. And the intensity is indeed proportional to square of the magnitude of the electric field. So I have been doing this. The blue thing, the intensity, the dark, bright, bright, that's the intensity. That is the square of the magnitude of the electric field. I just didn't have to solve Maxwell's equations for this simple enough problem. But in general, the electric field comes from Maxwell's equations. So the story is that for light, at least for light, the classical description of light is now reinterpreted to give the probability of where light particles would be found when light does manifest itself as a particle. And that happens whenever we make a measurement, when we ask where is the light particle? When we perform that question, when we try to perform that measurement, light materializes as a particle, it manifests itself as a particle, and then the wave aspect is useful for predicting the probability of where that happens. With all this said, we're now going to move on and we're not going to come back to light. I used light as a stepping stone because I presented wave-particle duality starting with light. I told you about the photoelectric effect. I told you about the Compton effect. So I had to bring that to a meaningful completion and give you a story of how wave-particle duality works for light. Now I'm going to use this story and I'm going to upgrade it to electrons. So the funny thing is that electrons, when you send electron one at a time, you also get this thing. That is absolutely crazy. You send one electron at a time, it's not interacting with anything. When the electrons accumulate on the plate or on the screen, you get the double slit interference pattern. So we will have to upgrade this red story to all other particles. Okay, so one other thing I want to tell you. Here, we were working with electric field. With enough effort, you probably can believe me that you can calculate the dot product of electric field with itself. I guess that gives you the square of the amplitude of the electric field. You won't have to do that, relax. In the next section, when we talk about electrons, there's no electric field for electron. Electron generates its own electric field, that's true. but um, the electric field will not be present in the picture when we talk about upgrading this picture to electrons. Instead, there will be some other quantity. It's called the wave function. So that's the pinnacle of this very conceptual week, is when I introduce the notion of a wave function. And you will be dealing with wave function from here on until the end of the quarter. And if you're a physics major, far beyond that. Wave functions are complex. So let me give you a very quick primer on complex numbers. And next week, we will spend a whole 30 minutes reviewing complex numbers. I just need to give you a quick primer on complex numbers. So when I do mention the square of the amplitude of the complex number, it will have some meaning to you. So a complex number, let me give you an example. So if I have a complex number, z equals 3 plus 2i. The way to visualize that is, well, you go 3 units along the real axis, and then you go 2 units up along the imaginary axis. And you can think of complex number as a vector. And as any vector, it has a magnitude. So this magnitude is the magnitude of the complex number. And the magnitude of this complex number is given by a Pythagorean theorem, like any, think of this as a right triangle. So this is 2, this is 3. And so this is 3 squared plus 2 squared. I can have a complex valued function. You give me a coordinate of the function, and the function spits out a complex number. So I can have something like psi of x. And it has a real part plus I, some imaginary part. And at any value of the argument, it spits out a complex number. And so when I say things like this, square of the amplitude of the complex number, what it really means, it means the following: f of x squared plus g of x squared. I say that so that when I do say certain things in the next section, it will not be super abstract to you. So for example, psi of x equals, say, x squared plus I sine of x. Just a weird function, right? Then the square of the amplitude of a complex number, of the complex function, will be given by x to the fourth plus sine of x quantity squared. I just wanted to give you some concreteness, because in the next thing, and what I'm about to say, I'm going to say things like this. This is just an example, okay? Not all psi's are given by this x squared plus I sine of x. I'm just trying to say that when you do hear this word combination, square of the amplitude of the complex valued function, you will at least know what I'm talking about. Okay, so with all these preambles, I want to say again, we're going to wane off the light discussion. Light was a stepping stone. And now we're going to generalize to any particle, including things that you think of as like pebbly kind of things. Like traditionally, you think of electrons as particles. You don't think of them as waves. So let's see how wave-particle duality works for electrons. Okay, see you.